Hello. Good morning. Ngadu dile. Ani ngadu nima sumbe ki ani tamshe sigin re rolling di gunzu che chowa che shuen yi. Ani dring jushi di zo ani du gi sangwa dan jewa yodewa. Dila du zambala ani sedu ngom rebe ki namsha dan jewa yodewa. Ani chi tedan terche an nangbe ki shung nanglo shebe ki du tarab ki nelu du tarab ki jodang. 대안은 시다 지게 뒤참모다 세두기 남샤든서 계자시 용도 삼발라 따줍단 대화 여비게 주시 배차나 유유진기 대화세야 소론들다 대안은 시 시제기 안에 직된 감기 춥지기 차 차슈든서 아니 요루요당 칸데스 요레스 다디 아니 고 유진라 마되비기 아니 유기네 룩세지 요레다 요마레 아니 여비 임베나 칸데 요레스 매비 임베나 안에 유진 나올라 나완다만다 나한테야든서 낭수든서 칸데시네 투부여레 낭수든 내수 발라 체벌 카르카리여레스 야든서 기계자 레디유요 손자 안에 표준 낭된라 롬니르 칭킹암 따들라 토나 윤킹키 아니 긴보 망부지키 토나 쳔부체디시키 다 주시 롭센직 비차디여레 제가 안에 땀시 칭킹 당부디 아니 조지 무스 차디여레 긴라 코라임나 제다 세리키 아니 좀 팅켄인데 세리키 내주 사쇼카 그나로라 아니 다 지좀 팅에 된데 차디 요리 이나야 아니 세리키 내주 약보신기 요베기 겸zel 때네 ngazuki leshi mangbu knaalola korangi gengol tuschiche ani nyamshu chenyong ketinde jire. So I hope that the translators are translating the introduction part, so I'm not going to repeat that in English. So I request first presenter George Musu to give your presentation. So it starts at 20.
Thank you very much, and thanks to all of you for coming. Let me amplify and echo and share in the expressions of gratitude to all those who have helped to organize this event, make it possible, make the entire program possible, because what an amazing thing this is for all of us. I would also like to extend a special welcome to our students. Hello, students. I'm delighted that you're here, and in fact, afterwards, if you have any questions, I'll be free to talk to you outside. Anyone who's too shy to ask questions during the Q&A, I'd love to meet you. So today I have two surprises for you. The topic at hand is the nature of matter. What is the material world? What is it made of? What are we made of in material, physical terms? And it's a huge question, so I'll take a small part of it and ask, what is the nature, the basic nature of the fundamental ingredients of the world? Loosely speaking, are they particles or are they waves? And actually, let me clarify that a little bit. I had some really good discussions in front of the posters 2 days ago about this very question. So what I mean here is the category of particle and the category of wave. These are categories that in the Western philosophical and scientific tradition go back really to ancient Greeks and probably before. And the philosophers and scientists were working off our daily experience. What is our daily experience of the types, the basic types of objects around us? And to simplify, they identified two categories from our basic experience. One is the category of a particle, a bit of matter, a thing, a physical thing that has like this glass has a place. It has certain properties. It's shiny like a glass is shiny, or has a shape like a glass has a shape. Crucially, with particles, you can count them. Here we have 1, 2, 3, 4, 5 glasses on this table. The other fundamental category is, here I call it waves. But what I really mean is there's something filling space, something continuous filling space, like a fluid, a medium. In physics, we say fields. Magnetic field, for example, is actually around us. We can't see it, but it's filling the space around us. And it's continuous. You can't count it. And in that medium are waves. And the waves in this categorization constitute the material objects around us. So particles versus waves, this is the debate that we're having. So one important aspect of that debate, maybe the most important, is how do we know, right? How can we tell which of these categories? How do we know really anything in our knowledge? And this is something we all in this room study and wrestle with in our daily lives. We have, of course, our powers of reasoning. We have the prior knowledge we bring to a situation, our powers of logic and thinking that we can apply. We have our senses. We have our scientific instruments, which are really amplifying or extending our senses. They're taking the world that's maybe invisible to us directly and putting it into a form that our senses can access. So, I'm pleased to report that in this room, there are probably hundreds of sophisticated scientific instruments. Our phones. These phones are filled with magnetic sensors, air pressure sensors, sound sensors, and light sensors. In other words, your camera. So everyone take out your phone. Everyone take out your phone. Even the students, please. If you have your phones, I don't know if your teacher lets you. And look at the back of your phone, at the camera. So underneath in my case, there's plastic, then there's the glass, and underneath that is the light sensor. So the light sensor, what is it? It's actually, in this phone at least, in most phones, it's about 1 centimeter square. So this is actually about that big, a little bit smaller. And depending on which phone you have, it's divided. This one has 50 million pixels, 50 megapixels. So 50 million boxes, like chess squares, that the light is broken down into. So think about what that means. It means that the light falling on your phone is divided 50 million times. So this is giving us a kind of microscope into light, in this case. We can maybe analyze the fundamental nature of light because we can divide it into such a small amount. So everyone go to your phone and go into the camera app on your phone. So this little experiment we'll do has two steps. They're both quite easy. First step, zoom as much as you can. Get as close to whatever. My phone goes up to 8x. I've talked to my friends, they have 10x, I've heard 5x, you have 5x, 15x. Just zoom into something, doesn't even matter, anything. Okay, step number 2. Put your phone, it depends on where you're sitting, maybe put it on your armrest of your chair, put it on your lap, put it on a table. Okay, you should see I've done something like this. I did it with my phone in the hotel. I zoomed it and put it on the table. No, notice, I don't know what you see on your phone, but what I see on mine when I do that is it looks grainy. It looks pixelated, right? You can see little teeny things flashing on your phone. And normally you don't want that, right? Normally you're trying to take a beautiful picture of the sunset or your friends or whatever, and you try to eliminate that grainy quality. But now we're going to look at the grainy quality. What is the grainy quality? Why does your phone create that grainy image? There are actually many reasons for that. But one of the reasons, actually in some circumstances, the most important reason, is that light is particulate. It's like rain. Imagine rain falling onto your phone. We had the rainstorm the other day, right? Rain was falling on the ground. It falls here, there, the other place. Hail falling. That's something like what's happening with your phone. Here's a basic picture of what that might look like if you're actually looking at your phone kind of on the side. What's happening? The rain, the photons of light, the particles of light, are falling on the phone, hitting it, and throwing out in this case, electrons, which are particles of matter. So it's actually, your phone is a way of turning one type of, or at least energy of one type of particle into that of a second type of particle. That's what we think is happening, and it's consistent with everything we know about science. So you can actually see particles on your phone, or not actually literally the particles themselves, but the evidence of the particle. That is what in physics we call, or engineering, if anyone has studied electrical engineering, it's very common, shot noise. Shot noise. It's particle noise, really. It's the noise that comes from the discontinuous nature of whatever is striking the phone or whatever. Now, I've done this program only twice before, and like many of my colleagues who've been here several times, I've had the honor of doing it twice, and both times we used a solar calculator to demonstrate another way we know that the world seems to, or the ingredients of the world seem to fall into a particulate category. Now, the solar, I haven't brought one here, but the solar cell on the calculator is a light sensor. If you put it in the dark, it won't work. If you put it in the light, it works. And what's crucial is the type of light you put it in. You put it in red light, it won't work. You put it in green light, it will. And Albert Einstein showed that that is evidence for a particle nature of light. Then there's other things you can do. Let's bring our sense of touch into it. What happens when you do that? How does it feel? Hot, right? Heat. What is heat? There's been a long philosophical and scientific effort over the centuries to understand what is heat, and our understanding now is that heat is the motion of, the random motion of particles. So when you do that, you're taking actually the energy of your arm and putting it to the energy of the particles. You're making them move around like that. And that doesn't work if matter is continuous. It requires a particulate matter. But some more reasons. Here's another one that made Einstein famous. It's actually hard to see in this video, but on the left are actually a microscope image of little, I think it's milk droplets and suspended in water. And they're hard to see here, but take my word for it. They're moving around like dust in the air, moving around randomly because they're being hit on every side by particles. Here's a fun one. You can actually see particles in what's called a cloud chamber, bubble chamber. It's actually a type of detector. You know how in the sky, when an airplane passes overhead, it leaves a trail? Those particles are leaving a trail in pretty much the exact same way in that detector. They're going through the detector, leaving trails. My colleague, Professor Goulet, actually has an interesting experiment, again with your phone. You can actually use your phone. You actually have to put a piece of tape over the camera, but you can use it as a very similar kind of particle detector, and you can find her afterwards if you're curious how to do that. Another way is you can actually take pictures. You can look at the particles, in this case, at the atoms. Now, I have to clarify, these are not the atoms of Buddhism. These are the atoms of chemistry, basically. But you can actually use special types of microscopes to see the individual atoms. Some companies have actually spelled out their name in the atoms. The particles seem to come in different, what I'll call a hierarchy. So the atom, the molecule also, is the basic unit of chemical reactions. It was actually also once thought to be the basic unit of everything. But then later, humanity, realized that the atom consists of subatomic particles. And then it turns out that some of the subatomic particles also consist themselves of particles, so subatomic particles. And there's a whole variety of those types of particles. That is another discussion altogether. I will say, however, interestingly, that the material world around us is mostly composed of 4 of those types of subatomic particles. So the number 4 comes up. The electron, 2 types of quarks, and the photon. So actually pretty much everything we see can be explained by those 4 types. But I did promise you a surprise, and promise you 2 surprises, so let's get to the first. And the first is going to require another extremely sophisticated scientific instrument. I think pretty much everyone in the room has even 10 of them. You will require your fingers. So what we're going to do, let me show you what it's going to do, and then we'll do it. you're going to use your fingers to create a slit. And we're going to use that slit to look at light. And what you should see, what you should be looking for, I should say, are lines that would be between your fingers. You can see it in kind of that circular thing. You'll see a series of lines like a barcode or waves coming onto a beach or something. In fact, that's quite analogous to what we're seeing. Okay. You can use many sources of light in this room. You can use the light coming in the windows, but we have prepared for you, due to the kind graces of the camera crew, a light. So what you're going to do before I turn the light on is take your fingers. This is the way I do it. Different people do it in different ways. I take my fingers like scissors. Everyone do that, scissors. And imagine doing that with their scissors. Then, to control it a bit better, take your other hand and put it on that. So what you're going to do is use that to press down and out and control that slit. You're then going to put your fingers close to your eyes, as close, and then open up as little as you can. And look for those lines. You can use, again, the different light, but this is actually a great way to do it. If it's working, but it's not working. There it is. Yay. This is very good because it's such a concentrated light. So go and look at something and see if you can see those bands. They're a little hard to see, but control your opening a little bit, make it come down, make it go, I got them. It looks like a comb, right? It looks like a series of lines. One eye, yes, I'm being bad. Linda, who's the expert on this kind of experiment, use one eye, bring it up to, maybe close one eye, bring it up to the other eye, like this, and look at that light source and look for that banding. I got it. Screen's light. You have your selection of lighting sources in this room. You have 20 different lighting sources. You can use this one, that one, these ones above. Screen's the best? Who uses the screen? The screen's good. And I apologize to the students in the room. I know you don't have such good lighting in there. If you can't see it, perfect. If you can't see it, do not worry. Find me during the lunchtime. We will make it work. This thing that you saw, this banding like a barcode or just bands, is the diffraction, what's called a diffraction pattern. Here's another way that you can do it. There's me in my kitchen, by the way, with a candle and 2 pencils. This is what we did in Gang Talk a year ago. And it's actually quite a good way in a classroom to really make this work. It's a little bit easier than the fingers. But it's the same idea. You use the pencils like fingers. And you get, by the way, you get on the right side, see that banding? That's the sort of banding that you get. And in this case, it's actually colored, because that's part of the phenomenon. Diffraction is a wave phenomenon. It's suggesting that the category of wave is how we should be thinking about light, or is one way we should be thinking about light, because it's caused, as these water waves are caused, by the ripples in the wave lining up with each other or not aligning with each other and creating patterns like this pond. So we kind of have a little problem here, don't we? Earlier, I gave you all this evidence that the fundamental nature of matter falls into a particle category. Here is an example of how light, at least, falls into a wave category. You can do the experiment in other ways with material objects like electrons. They, too, fall into a wave category. So what's up? How do you do it? Contradiction! Sa! Contradiction. Nature. I've contradicted you. But no, right? The contradiction must be in us. Nature is not contradictory. It's our understanding of nature that must be somehow contradictory. Our categories of particle and wave or particle and field seem inadequate to nature. And this is the contradiction, the insight that quantum physics just tries to describe and to some extent to explain. And I have wonderful colleagues who will describe many of the the puzzles that come from this understanding and that the quantum physics presents to us, because this contradiction creates all sorts of puzzles and paradoxes, and your mind just starts to explode. And that's really cool. Surprise number one. Two contradictory categories, because the wave and the particle are not the same. They're contradictory. One's in one place, one's spread out. Here is one way, and there's many, that this is manifest in our scientific experiments. Unfortunately, you can't do it without your fingers. I'm sorry. So suppose you had that diffraction pattern, or a similar pattern between your fingers. There is an example of it. I've blown it up so you can see. And you begin to dim the light down. You turn the light down. It goes to dark. Everything dark, dark, dark. What will happen? This too will go dark. That's not what we see. We see this. Start with the same pattern, turn it down. What's this? It's dissolving into particles. Here before us is a wave pattern and a particle behavior together. And the other esteemed colleagues of mine will walk you through some of the meaning that has. But I did promise you a second surprise, no? Are you ready? Let's imagine a bunch of particles and you start to take them away. Oops. You start to take them away. These particles are going away. They should be at least. Yeah, they're going away. Bye-bye, particles. What do we have now? What do we call this? We call this it's empty space. It's called a vacuum state. Empty, right? And in this kind of metaphor that we're using. So, I should say, be careful, that if the particle category applies to the fundamental ingredients of the world, and there are no particles, there's nothing. You have no objects, you have no activity of any sort. It is pure emptiness. I'm curious what you think about that. But in our theories, in our standard model of particles, we call it the particle physics theory, and in our scientific experiments, we actually observe this. It's empty, no particles, but look at it. It's filled with activity. It actually turns out the vacuum in physics is the most active thing of anything. And yet it's empty. What is creating the activity? One might argue that we have the particle category, we have the wave category, neither is working here. So maybe there's a third category that we don't know about yet. And that is my surprise number 2. Thank you.
아니 gen George lala 아니 투지 치스 슈이 제가 아니 지게 제등공 감릭과 knang로라 아니 지게 두그랑 신시야다 랍그랑 신시야 아니 랍두 칸야 메베케 동상기 반항기 나림베나야 아니 자와체밤 아니 쯔와체베케 아니 지게 칠레딘데 아니 통야요베케 니수콜라 빼고송송 디젤라다 제와든 정좀 문tun리로 아니 디젤라 아니 간소 담신 바니와디 아니 게시 탑글로들라 차기요 사베 차네 게실라기 아니 지게 낭베 슝니시베게 아니 두 타랍다 아니 든주기 다 네당 든주콜라 셰타 테다냠도 아니 게실라 주릉보 아니 세둥 감릭베기 아니 게제셰 칸든조 아니 규이 베기 좀 때네 아니 디니 숭저기 삼노당당 칸데스유메다 든조 토라 아니 담시치그레 아니 게시다빌라
Yes. Okay. That's. 직된티 시데테베 konsalami namrin jangwe jawang bu chola kuja ngwendu tangne anen de pepe jamne gindu gi de dan ane chojawa sangmalo le yata chamri shue tatine tuzu mewa yinza kapduk ma gozuk shana sams 다 nga 가산 주시 데 까마게 송야 제나 다 낭베 숑게 뒤게 남샤 데즈 데스 샤나스 당부된 데다 부지레 이나야 다야 제라 가리샤나 뒤그레스 당 간당에 지 가사간에 지 렌즈 체제 엔투와 진주시 데스마 슈야 베스슈이 로아 다 ngaran din na lo la jushi jidan chen na zawa mi dirsa da uchi sum yu nangbe chung ne shewe duden gi jing gi dum shi da su jun she da chik che dine duden sen na kare se ya de chik che di duden ko la nga zo chawa de duden ko le je ba chen kare pen do yo re nga zo tu jen so gu ma re kare chi gi yo re se ya de che en tama de la ya da chik tingsan chen ri gi na lo yu dan yu jeng gi de ko ta mi se che dung ngam chen ri gi na la chik yong gu yo re di ko la ya sam ju de se da chik che na tum bo yo sa re 다 당기 다 세리기 돈의 제비나 고 가르치고 그래서나 로다 되서 된기도 와 당한저 때에 매자 중나당아디 곰티고서 삼삼대죠 당한저디 콘저기 유제 처대 한저기 다 제곰다 조금 지야 디송자 아니 다 오늘 제나 곰자고 해야 저래도 되다 곰잡되나 된 가면 저좀 당으로 하시 딕사마레 때만다 제가 다 이내래 다 당다 간기 뒤워지 되게 그래 세리기 돈에 뒤기 남샤도 간데 시에레스도 주제 배제당 안에 그 니레 초연나 당 시에레스 다 오늘 간저 직 시에야 되죠 주제 철라 당고 니람당 드링 시에게 여러베스나 디아 마레스 코람 직 가리 여레스나 시제네 숨 세야다오당 직 유일라 시제네 숨 제야당 되네 직 간저 가르서 그래 따조디 덤버시 남샤 철라메든 가서 간살메든 철라든 세야당 디렉 돈에 안에 고비게 배제당야 돼 랑중 그리고 실라 소바 다디 배주 제변 나로라 주의 시제 나로 주레야라 아니 나란주 주숨게 댄스고 대한 대원이다 다 도스 제네 제 칼라간점 제 신조레스 다디 신도 주제나 시제네 다 코비게 앙단데서 댄라 밥두고 말이디 지용게 남샤제 가젤레기도 남주 색초 그래스 저다 당보딜이야 다 genjo지라 송바나시 직제나 간저 단다데도 돼야데도 하람 다 얌첨부시 저게 이제데 직제나 양 간저라 가시 닝바 인식레스 고서 저게 베나 곰블루도 지다두블 콤베 틱젠바 시게 뭔가 리과 사바데다 동네지 남사바 튼서 투미지 요바 통 툽시데 양 가시 얌차보도 된데 답베나 된데 용시버레스 대가나시 가브레 체리게 당기 갱게 덤바나시 라비앙레 뒤야인베 시드인베 소레 개와인베 소로 대세 자마투바 돼야되죠 가브레 체리기 딱제 심죽 체네 된게 열라 가브레 낭베 리글람 페저 다용데 대세 자마투베 내다 남바 코랑게 낭고레 리글람 피게 되나 줌제유베 소레 데데나 줌제유베 소레 줌제니게 바루랑 겐두 도제 ngobenelu kanlaya yang gendu inbe sonde de ania yores 다 수 지당 낭주랑게 제장 ngaranzo da shedang de karesna da jungshi gi duidang de zo shegi yorwas jungshi gi duide zo shegi yores da yinaya nubjo nalo la ya jungshi du kor chedang ji shebina na ngamo gi da gris da dwa gi da rub de zo re tengrab gi cha shana da zaze da di thone du thame thone de she ja gore da dizo be karso re ningba da ujere seya dinde ji le de yores da da koran yinaya kabre shib za bo da yon de dinde cha gi yomares 단다 간주기 두탱게 남샤 셔야 되죠 양 다시 사두 메두추도 오 메두 망고 전하고 매차도 세야도 대시 디지고기 저기요 말했어 그런 게 나로라 대시 마십다 도연디잖아 아니 즉 뉴바당 첼레당 아니 제두사당 딘데 돈에 대시 망고 시작이 요래 스페셜샤난디 낭베 춤다에 기타 좀 가시 다 제라마에 춤다네 용디잖아 정말 뭐부 첨부되죠 간데서 주비요나 디 총르 당제 땡럽게 세르게 따당 나시 전에 따둑게 돈에 삼로 당제 제요레스 디 제연도 안에 담에 따둑들랑 간주 제두사 삭두 안 두두세두 땡사 제비나 elemental particle the atom the molecule 디게 따다도 제레 요레스 제단다 디존나로 트리워지 간주 가리티요레스나 두덴테조 간갈로 마뚝뚝뚝뚝뚝 나다 탐에버 두비야 요레 간잠진에 두그레스도 다 제라마에 tum다 제나 참해질로 툭고 그래서야지 다 아니 계직이 이나다 가리나 다디 간에 연구를 장래 나랑도 간사 소소라 나가스 슉첨부슈 라연데 지도 바지래야 나스드 장래 도와지기 저거 나를 옆에 처나게 간지 시대와 나시 치르기 쳐라 따연데 숙쟁게 오번 데서 자장을 갱 랜드직 제나만도 알레 더 제리베 가르치나 디직 제가 저 왕한 체리 보니자 더 제가 다 속쟁게 쳐도 직탁다 동도 타마딜다 밥사직 고그레 삼야데 네 간에 연구열에서도 최담제 랑경원에 두고 거래 템버투버 타르동네 제나 따던제니 니사지 고그열에 삼야게 삼로디 요와 인자 다 두된 참에 계직 참에 타르동네 제나 딜로 투고 그래 삼야 네 간에야 망시딩니 중조래스 다 이내 디조 티와 나로라 까브레 아네 두된다 니기 바루래야 다 단다 때나다 베디네 차잔 자데 까브레 디조 두된데 조 추인 자요나 똥바레요나 디바루 가레요나 디네 쪼바 빼망부 쪼요레스 때 쪼바데조 까브레 어다 디조다 다스 쪼데 인게선 디레요 마레스 딩랍 체릭 나로라야 빼차잖아 만조 잘라디 딜라 투고요 삼고요라 오네 투고요르베스나 체릭이 따두고 터네 투마도 셰 투고요 말 할람 투고 마레 랍투 가이스나 타마 마마레 온도 장라 두텐라 투용 록두라 투 록두니 바루라 투 슉 잠네 비자 잠네 타마 톡 마레 제단다 디조 딩랍게 때비나래 어디 알레 오네다 투고 민도와스 나란 정에마 셰데야데 nga dungdu ane ta nga duse dongbe khadola nga yukde nga laya thugre mare matuna da kharchene thagre labdu nuwa june da thagre lagorwa ta tegara konzo terigi kharchen lagorsa di barula logdu ni di dukse de yuwayina logdu ni di matuwayina logdu ni barulan dewa kharchen chigorse du kabre udu tane kabre lab tane dide dewa chigore labdu duden laya ane dewa chinyegi duden 시제 독시체네 연제 당고야 근데 남샤 먹고 레데요스 제가 엄마게 수준게 따릅데도 찾아로 세티보라 맵이 이내래 갑조데 너르게 매바데 제베 고 갑조데 가왈레게 요바데 양 아주 또스 톤투 그래 해삼고도 다 디네 두댕게 세시 템베체 다 두댕게 세시도 오제 단다 아주 독스마 템베체나 세르게 토네 두댕세야데 춘주 체연데 아주 낭베 슝네 갈라 간잠직 체투요 원베 슝네마 penang azu jakju rebon lukdan la nyeseri du da somadan seya de tak ngomba zhe de le ya shenda menda ge cheju shubji yore nge samna gari yore sena namsha gari shebadi sugjen rabwe tone khung shige gre khurang ge bagjo penang azu dutenji re lana tharmati sorchik sidu jang la che seya yo sorchik che seya yo de sorchik le du gaja yeme tanga ja yo de du chamode gaja yeme azu angji jap chojo chabre 내가 나신 ngomba zhe na la keba ji ja du jang la penang azu de la ge wa 가르사 안에 땅 안주 nendu luge야지 가서 단다 대시 자기와 땅에 책대로 로마서 갑도 되려야 남지 두고요나 갑르만 제가 뒤치도 잘라 꼭 깨바이나 로 가서 지자 딱다 지자요 고네 슉바르 깨바 차바네 뒤차바네 똥베바르 뒤차장지 대시 잡도 강가 남샤 안주 텐데 켈린 두고 요메 미시디 좀시디 할레베 차창고요 제가 뒤지기나 안주 지자도 다 단다 뒤지자베 원도 담비나 낭베 슝네 셰베 두 타랍 라비아 디 체리기 토네 셰야기 간저 다 가르스고레 두텐스 애톰스야 딜레 테즈 타워 메나 삼삼다오지 이나야 테랍기 체리기도 딜레 충아 하장 기타 곱두다 디조간라마 도투고요레 디 간저 남샤디 디 간저 켈랭고 고 딘데기 토네 이나야 디 중네 티와 가리오레스나 디 간저 가리셰다레스나 지라모다 도데베 셰다 두 참여기 셰다 시제 뒤래야 충슈지 열에 니네 잠고 레세야게 좀더 오메셔다 다 이나야 디 저거는서 됐어 제가 다 딜래야 두된 참여를 가고 당고 자야도 로마야 되와게 시작부터 나라 계시 두된 자네 거라베 차체야 매비나 잡단 뒤 용기 말에 되네 고바주 산에 보싱기 말에세 딘데 셴네다 마 가고 잡네 두텐스야데 베데 가두이나 차체주고 그랬어. 뇽달라야 아주 삼로 따위나 콜로 샬로 눕장게 차체고 그랬어. 베 두텐이나 강가로 차단 제고 그랬어. 안 덴데체네 시자 탐제 베 차단 제코 차단 차시에 뜨베 데와 툼네 덴데게 남샤 줍다. 어 덴데 송요랬어. 다 디네 아주 지와지 가르차고 그랬으나 디 가란 줄라이도. 오나 다 tum다 고멜룰라 두텐도 총르 따네. 두야 자니요 말베스. 바데 가제 총르 따네. 디데라 멤버 소리도 먼저 따두게 삼로 토네 소소 삼로 가제 땅 투베 디츠게 자시 그 투베 러시아기 자시 직켈랭고 직대 가래서는 뒤총르 따나 tar nube ngo dugre se tanda geng te ya de chenga dingjo marda geng di na lo tongba cha du do di te tama che lab ge ngo chen di gare se da ran zo ge de re sha pa do ye do na la de song do pena cha sha na kun ga wo pena 취향 착발 주네 착발야 줄주바이 최저라 되식 세감 락바데 사시 첨부 줄도 참모네 세뒤 참모네 뒤 타랍지 발도 줄도 세테릭바체 속신도 타외 타도데 차드윈레 주바이노스 제당 간저 저저 나라 차드바 아니 간저 오바 단다디 도와 나라 죽바 아니 둥거 나라 차제바 땡에덴스케 메바 덴데르 와코 인도장라 kungaos kete du tarab dini gobe namga tongba juna namga tongba le sugi namba chuba juro stati danda tagda lawyagi kesi du pe chungsho dizoya meba soyagi tapsi taina ngoye nechula sobeina ko tongbe ranshi nube ngon dugre seya sonde namga tongbe ngon dugre seya sonde che ndonala twende do jadanda di kor di shumoga che 다 디네 ngazo duke korte nangbe duke korte disamrebesana tsane mares nangbe duke korte la pena du thukma tu cheba cheba pardon yo ma yeto cheba chedo na do shudo 제라마에서나 두개 잔이 요 말에 pardon 요레스 디안 ngam serikda dizol tunya do jor do debe sewaina pardon yo baina tongba di na lo la we da dizol zu du gru was 근데 인도 장래 tongba yo 말에 토야 요 말에 수도 야 뒤다 dizol 딩랍게 찬네 제바 빼 망부 제야 요래 먼저 의뒤지 도와이나 의뒤다 뉴티노스에 도 가르치는 누구 요래서나 뒤 코란래야 록뒤 쿠르메니 차치라 그러와 차치 매비나 코 도베 가도래야 오버 셴발 견자게요 말 다 당기 간저 야 쿠르 연전이 요바이나 토고고 요마다 도 갑래니나 시제 담라 레바 잠기 펜주 비자 따레 제야다 그 남샤데 톡두고 요라 제가 딘데 망보다야도 내가 나시 나웨 뒤 문베 뒤 딘데 다 저나라 망보 체도와 디조 오늘 전에 직전에 땅안서 수준 그 돈에 마고 같이 문바세야 되도 뒤네 잠저레 삼네 직 좋아래 양당 오늘 등산 거라다 사 배직 안서 직게자 알아서버려 시에네 등산 시에비나 다크 매터스야 도다 다크 에너지 수두 장래야 직 딘데기 보관 당보다 딘데기 남샤 망보 나로라 뒤기 남샤 직래 거래 건조 간데 두기 유맥 제가 딘데 게자 시에버래 딘데 직래 야 바바 도메기 쇼나로라 넘버 로가 직 시에비나 야 뒤세야 되도다 왕부 뒤 디조 다 지나가서 저 나로라 다메타라 두제 제스 디강래야 아니 왕보다 디조 뒤자나 줍시다 근데 차도 그래서 왕부 뒤다 디조 직남셔시고 야 바바 도메기 숑카시에다 디조 나라 최기제제기 뒤 최기제제기 송아 디조 나로라 야 뒤뒤다 뒤 망보 직시에게 먼저 뒤그 꼴라 빼 할레베 단다양 베 늪석바나 시체네 건조기 다와나 신 가서 숑로 나로라 슈부다야 여바다 오지 단도야 여바다 오지 다 차상 간다 외베 내줄라 딩럽 나시 젠던 통에 메시디 뒤기 남샤 단도 망보 여바지 셰고도 삼 다디 낭베 숑기 뒤기 남샤 잠제 오나 뒤기 오 가르세지 땅 아주 수중이 나로라 당기 갱기 나와나시 뒤스나 토야 여된죠 닌독스 동가 잡이나 고란신기 직 파츠 파래야 윤조 딘데 장발은 문제 지금 요래 요 말했어야 돼 제가 단단 아주 나외 뒤레바 문베 뒤 파바 도메기 차이나 의뒤 따부디 중화 제레 투바 말했어 중화 찍레 투바라 말했어 데 중화 찍레 투바레만도 중화 뒤세 제갈레 투비야 말했어 시생아랑 저기 뒤세 제세야 돼 제제비나 아니 드라이 가바나 티 뒤세야 도다 저 간데 체네레스 누베톤에 되세 자기 요래 아니 오늘 람비게 지금 마세나 로가 티베제 가보르다 딩럽게 세리기 돈내고 베시포르스디 마세비나 딩럽 세리 돈에 담아 마페베이나 시대 좀 시직간을 봐병 거 딘도 양 알아서 저바줘야다 요래 빼나 차샤나 알아서 룰라 분바디 가웨 녀렌 두구리 베스는 누구 말이디 시대 뒤 오늘 또투베이나 분바 소야게 제디기 듀텐 애톰 대조게 코 가와 소야를 베죠 당에 요래 타메게디 애톰 다도 제이나 가족이 녀렌기 주인데 페버레베스 당세 당이나 당해 유시바요 가베 분베 녀렌치바 요르베 거기 제준데 그 제준 오 누구도 와서 시제 두기 간을 파비나 누구도 와서야 다 대조 간제 간조 제바치야도 빼망고 요사레 삼고 근데 제리 코라 나로를 갱글라와 나시레 뒤시야데 당보 사정 예전 임바 지기 툭나 파래야 윤조 근데 지금 삼로 땅에 어디 다 단다 딱제 심주 망보 랍임베 남샤 망보 땅에 뒤시야데 담도니 녜만나시 멤버 덴데 땅도 제가 다 디게제 시한데 아니 가란주 둥고게 나로라 남게 뒤 세야데서 강가로 인지 미지 숙쟁지 고기 매봐 코바 지 단데 숙쟁게 라베 쳐디게 바직 바팀니 아니 누뱅 오 껴르두스 숙쟁 오라 트야 윤조 딘데라 뒤기 남샤 지기 요베 선다고 딘데 레용고도 제가 디조 직제나 갑죠 디조 얌사보레 삼고도 디직 쳔바레 제가 아주 둥거나라 차샤비나 남게 뒤 동베 뒤 내가 나시셔 제가 디올라 타마델 단다 닐스 보르기 직 랍도 everything we call real is made of things that cannot be regarded as real. nganzo ki tanda thong debe ngobo sukjen raba kanga chik sashing tekbe number shuji yo deba samsam di shite zomshi di pa zega du zangle ya chik Koran chik lab ki sore tham do nye sore kabre tongbe ngon do nye debo dinde chi che du zangla chik ko bige shite zomshi di chik dire se zugu zugsa mebe sore chi raba o di chik shina samsu da di jab che chezang da di ngarang zo peji chik shungi nalo la namde ki shungi nalo la wangbo de zo sukjen ki chene sungme la doya dang yang la yang chu nube ngo chuja karsa suk ngo pya yoba sungbe sodawo ngombe nalo la wangbo de zo du sungbe sodawo nganzo uman jubba nalo la ya ane rang namshi tenji nu te la wangbo sukjen mikje chawar dos labya de zo le on de tat pete Einstein ke namsha gera simbo nuba da de ze ngon doya yosia de zo kabre chik chena dawo mena sam ta du ki chane sigior da ko namsha ki chane shi ke sigio mar shize ke rabzam chik dawo mena sam ba chik dos ta dine shuya dire ta ona nganzo du ki namsha de zo khande res lavina tsere ki du ki namsha la durwa ina kon reshe jada ta ina nganzo ki ta du ki chade mando shirum ki chade khabore tsere ki nalo la du thamo chi la nuba khaze yume 거기 원에 즉 로라고 즉 슈가제 되게 유매 안고 가제 dom나 가war레기 유매 니도 제도 항상 십자보 열어와 디 열어 디 제르기 개베레 먼저 다두기 돈에 된데 제투비야 거래 요마를 럽저 지금만다 다 이나요 제르기 돈에 오나 딜라 때네 먼저 메젤라 랍자 가르래 요래 메제기 제당라 랍자 가르래 요래 디 항상르기 돈에 요마래 공오보 거라비게 주제다 디저 돌라 제야데 마도 지래야 디 가르제네 계기 요래서 라이나 빼나 nangpa sanjewa wana dui kola chudo dinde chene karichi koresita dui tawara dezo nganzo dango de nganzo gishi de karsa ishi doje dasi dangpa nashiri di simbu tanjimba ngela gaya nyeko mese revesi na dinde mardas di nganzo karichi koresina ale dinde chi reidwa dinde yindu nge lola kante si chargidwa jundu nge tangzi di kante si chegidowa dinde chidu nga ta kante chegidowa tela tene nga lan dosha shedang kante yongudowa dinde si yongdu zangla nganzo ki tama de gawa pukaresina nyamlengi tola lakbar duda pengo babalu duge tanda di nalala jibu sami chumayi mimi lungmi nangami namshi mayi kuime na tele shena jibu kam dung dube sir yanda mayi che tishin kam ne re yang du chir yanda ni mayi sidu tama ane kam ke tama saju melong la lewa ina deyang sebi ina kawa dugures pa takdun zene dine zay yondu zala ale ta nganzo namju zamdeya dinde jik minduwa 캔사와 라 사미야게 삼주디야 제온데 신에 nganzo ta ale 직 ngaranzo 남주 짐바나시 페나 ngan가스데 슈 요섬데야 되죠 angone 랑 삼바나시라 요사 마르와 사미야게 삼용데 nganzo 추 가와레스나 데 덴중다 다 다메바다 메다베 고아니엘라 페나 뒤 담모 되죠게 제제 땅에데 당고 직 섬소에 단 통야미도 뒤 충슈에 되죠 가시엘로데 까르자 세겐 슈부 된데 담모나로라 다가런 직도 그 배지직 가르서 오래 깔짝 자세 담으나라 지그도야도 다야 저바두다 뒤들을 때는 미다베 남샤 제위나 단당 아주 보디세도 포턴세지 디야 냠구도야 요 말스고 빠데 야 빠데 로추 정마 깨바 망고 된데라야 치로기 숙제 마테베이나 요자네 메바 레베스 띵 아주 깨지기 요도야 디 요레다 요 말에 뜻답에 랑신 인다 마이스 아주 가르서레 치료베 숑나로라 뒤답에 남샤지도 디 항상하게 되도 등사지나 제릭나로 줘봐요. 포텐시아디 디게 요래 요 말이스. 냠구 고 랑중게다 디게 디지도 뒤 참모데 나가면 직된 감 정보 줍디기 보디디 단대 보디디 가라 레스고래. 디디 갑레 고 텐드 딱바다 이미 미시디 내가 딱베 랑시지 셰요 되버래. 양 먼저 매선 뒤다 드롭 콜게 되죠. 제나 세튼디 쇼지레 되어라. 양고 미닥베 랑신 쇼지 삼로다 유디 먼저라 디기 토네 따두게 토게 랍잘래야디 쇼지요레스 데 인장 먼저 두댕기 토래야 주도 제고 개게요레스 두댕 토래 주도 제야 되죠게 먼저 가리신 두고레스나 오벤넬루 딜라데네 낭로를 잘해야 돼. 먼저게 낭로게 유쟁 좀바 칸데 제기도 딜라데네 제야 디 제도 장라 딜라데네 가라조 용서다 당지 제지도 디 체릭 발라 메바데레스 다디 제장 딜라데네 먼저 담아데 가르치고 다데야 즉 요레스 대바자 많이 받다 등랍 가르치고 그래서는 다 지나 동반이 고뭐이나 근데 가야 전에 니주메베 따로 되서 고뭐이나 아니 루심을 좋아 가르치고도 했을라는데 다 등상 가서 랍쳐져 매래 건조 두제게 내용 거와 다 두제게 내용 되잖아 다 가서야 근데 그 딱제 심죽체네 단다다 디조다 신행 고조 버레 베나 단다디 딱제 지기 갈라 그래서나 딩랍게 템바니샤게 곰데조 슈위직다 달잡친데 여러와 이내 단데조 슈위직 단다 십자보 이메 메시데 좀쇼 가시 나로라 동니 고미야데조 직잖아 템바니샤 곰발레장 먼저 직다 가르소레 심감 트레덴다 데조라 펜체와 유사르다 세야게다 딱제 심죽 신행 고중에 누구래 저단다 디조 뮤티니 가르서 우리 나란다 오지나 다 디조 간데지 레기 나삼네 소소라 잉요야게다 뒤서직 된데지레 샤상고 다디는 디제자다 디게 겐라 넘버 솔로 도나치도 슈바이 제둥원감다 직 가조 낭베 바루르 둔조게 뎁된데다 겐라 콘조 다이 낭게마 닝바 타오 피직스야다 오다 군두인게 차데다 디리 카셰 낭다 원감 세릭 란다 낭조 바루르 둔조 망부제네 세릭 바랑 틴조 단다 딘데레데 요레스 안데 벤나 차샤나 Tibetan Buddhism and modern physics Victor Mans for example the gengamala during the 단다 가조 베익 더 로로이나 먼저 셰엄자 마인바 대브란 세릭바랑 세동공감 세릭바랑 게 틴조게 대브데조 식투와이나 벤도 첨보여레 겐라 주르네 단당간조 로에 요레스 베이나 다디 담아들라 되조조서 베조면은 아까마지 오케이 야야 다 까마지 로인이로 sorry for I back to 1 minute because yeah 다 딜라 간조 남주 군두게 송구도와 ane chedung ngam cheri gi tawa de mama chedung kable sem zambe ta du dabo sheg du da sungya de kare yoresna dangi geng gi sungu duwa du gi namsha takje ji gi thone du gi namsha tong gi yore takje ji gi thone lab gi namsha tong gi yore ta de zo danda ngam zo raba ra be kan ta thuje ran na lo la du kan re tanje danda ngam zo we du de zo tan du jang la we du pet sa mang bo devla tang gi yora we du kan jik jik ta yon du jang la yam chen shi de mang bo ta yon du yang da ga lab number 2 yon du 우군이 요바이나 뒤직라 우군이는 주고야도 다 딘데게 직지도 다 뒤직 뭐번일을 요고 다팅 우고데 간엔 주만 주 다대성에 주제 14부게 제시오 지당 말다 제도 딱제 제네 뒤데 간엔 주고도 왔다네 뒤데 간엔 주이면 시와 대체 치료될 가르던 거 그래서나 뒤게 넘버만도 랍게 넘버도 된 거요 말에 다 간엔 주이면 마시 받아 마대 공라 가르던 거 그래서나 랍랑 게 넘버도 된 거요 제단 지단 세릭 버서 남시 걸 시엔도 천이 요 말에 락버도 ngogam 세릭 버서 남시 걸 전에 없다 쳐고 이나양 단 딜레야 observer effect 지 요사르다 따오브 숙젠지 요사르다 쓰는 거 딱제 가제 제비나래 등게 여러 바데 되던데 잘 알레 캔서 딜레 딱제 진행되게 간다 미인 거야다 요 말에 주제 던베나가 심죽 진행되게 비기 아는 뒤델은 로살라 가르제니 숙젠 되게 그래서 디체네다 디고르라 망아 겐게 단다 겐다 겐팀 tapе ngone thone kona number so inada bede tologe da dir kharan thola jangba chinjo inza thiwa thithumna pe mesi khogabreda aranzo namju da shemza maimba ngone zerik ba soge garishege doa di thiwa thya ko khogabre chesa dijiche da dine chigrach chigla konso garishigo resna da gesi tokship jebe gadola tokship je ondu labge number di durne duge number chage yoina 답배차샤나 단다디 웩나슬람니 세릭버 깨다침보고 노뱅공감 세릭의 자가란조 직동급자 두줄에 숨로라 공기 세와 있는 남시랑 주도 지기도 남시랑 유전의 숙전 되기도 자자자 캘린 거래 공기 공 간데 캘린 것은 변한간서 족보직 공기 족보직당 공이 딱제 심주간라 대요와 이나 다 미지기 배치로 되어다야 콜라도나 심주칸다 강가로데 단다디 뒤단랍 녜메게 내버체 콘조 다 간사직라 다 이게 딱제 심죽 간을 미지 두대요. 미대게 딱제 심죽 제바다가 tum데데 코비게 듀 간엔 로이메 텐디 코데 듀게 넘버 템바 하코사레 콜라야 랍듀 녜메게 네버데 마레 쟁너게 네버데 코 듀게 넘버데 타쳐사레 이나 칠로게 강사데게 듀데 간엔 로이메데 되게 하마고데 콜라 단도 듀다 랍게 녜메 데요로 데요데 장래 듀다 랍세야데 ngobeting라 요레 강사 소소 통화다 주게 요레스 이게 나라 덴조들라 뒤달랍 타 쳐차래 강배 나라 덴조게 세릭 받들 다 강배 치로를 대네 tro보되게 따용데 뒤달랍 녜메 차들 단도야 디지도 장라야 다데 좀쇼 가시 나로라 세둥공감 세릭 시송 제나 ngo보랑은에 주게 요사 말이다 따오브 숙전 자게 요사르다라야 계자들레고 딜레온데 단다 데 군두게 갑레도 딘데 제나다 심잠베다 룹다 안에 데스 타냐고도 와서 송네 송야 데레 디골라 망아 겐락 송그레슈에 토체나
Gish tabgila ane tuji che si shui ane DJ ki ane tamshi chingen di gen ion dusham chagye ane genla gi ane tanda chenji ki kanyo se ta di tanda ge thapkela gi ane tamshi ki jugjong rang chagye yor cheza ta yugi nezu tub madu se di tawapyo ki chigi yor da yo mare se ta tanda chenje manje se di ko chenjing khen ki ane khangsa yo me da di chenjing khen di su sha go re mare se di zu ki kejeli yo songzang 아니 지게 따와벽이 슈진야 라이레라 대가나시다 천지기 강요세야 디야 아니 고 낭도 직직버시기 요선자 아니 디골라 아니 게니야 시레 아니 게니야 인벤나 단당아 주디 두기 상웨긴 점든 디 나로라 아니 룹디 징이 기긴 소지 차디요레 아니 이안 please it's your time now.
No, I just wanted to, yeah, okay. Well, I was going to, let's see if the slideshow works. No, it doesn't. I don't know why it doesn't. No, but it's, yeah, you need to switch the displays. But that's all right. I'll just do it this way. Okay. Yeah, but that's going to, you have to switch the displays. It's okay. I can just do what Topka did. Yeah. Don't worry about it. Well, I'm just Tashi delay. Nimingla Ian Yin. Debo Jimpe. So I promised Geshe Lakdor that I would learn a little Tibetan, so I'm trying. I want to start by thanking His Holiness the 14th Dalai Lama for his vision of creating this program. I want to thank Bobby Sager and the Sager family for funding it, and also for Geshe Lakdor for all his leadership over the years. I want to thank Bryce Johnson, who is not here, but he great leadership over the years. And of course, I want to thank what I consider now my second family, and that's Karma and Palden and Tsewang and Trinley and Tinley and Chunyi and Lobsang and all the people at the Science for Monks for being such wonderful people and feeding me so well. And of course, I want to thank my students, and I really appreciate the questions that I get. Yeah, I'll just do it this way. That's fine. I really appreciate the I love the questions that I get when I teach. So I've lost a lot of my time, so I'm going to just kind of talk quickly here. So Karma asked me to talk about the quantum measurement problem, and I'm actually quite thankful for Geshe Topka and George for introducing the topics, some of the topics that, of course, they're now completely in Tibetan, so I don't even know what I was going to say. Well, I thought Sewang was actually going to put the English next to the Tibetan. So, okay. Well, anyway, so I think my first slide was about waves and particles. So I'm supposed to talk about the quantum measurement problem, and I'm fairly certain that this was supposed to be about waves and particles. There we go. Only the first slide. Okay, that's good. So I'm going to go one back here then. So I think the first slide was actually about particles. So the second one is about what George didn't mention is that the wave nature of the wave description of stuff is related to something called the probability. So I think everybody knows what probabilities are. If you flip a coin, you have a 50% chance of it landing heads or tails, roughly. Or if you roll a die, you have a roughly 1/6 chance that it'll come up any given number. So those are probabilities. And the wave description is related to the probability that the system that you're looking at, the particles, whatever, are going to be in a particular state. They're going to have particular values associated to something that's happening. And this relationship is called the Born rule, after a guy named Max Born. And quantum systems evolve over time according to something called the Schrödinger equation. And the Schrödinger equation, the solutions to the Schrödinger equation, it's this fancy math thing, and it has these solutions, and the solutions describe a wave. So the evolution of the system in the Schrödinger picture, there is another picture that you can use to describe this called the Heisenberg picture. But in the Schrödinger picture, it assumes that the system is described as a wave, and evolution of the system occurs as a wave. And because the wave description, and the wave description, which actually this was a previous slide that I think one of the ones that was completely in Tibetan, the wave description, what it describes, because of the Born rule, we think of it as describing many possible states. So because the wave is related to this idea of probabilities, it describes many, many, many possible states. And so as the Schrödinger equation describes the evolution of the wave over time, we think of the system as being in what we call a superposition of all of these states. It's kind of like it's in all of these states at the same time, in a sense. Or that's one way you can think about it. And Tim's going to talk a little bit more about some of this stuff in the afternoon, but that's just you can kind of think of it like that. So oops, oh, I got to do the down one, yeah. So, but what happens is eventually, of course, aside from, a few cases like George's little experiment here, when you actually look at something and make what we call a measurement in a quantum system, it's a definite result. And usually, maybe not always, but usually it tells us the system is in one particular state. So it's in one particular state. It exists as this. It's never in all these possible states when we actually look at it or measure it. And Geshe Topka talked about the observer effect. This is a little bit like that. So, and in fact, this is related to that. So we can think of the results of measurements. So when we make a measurement, we can think of it as we're in a particle-like, it's the particle-like nature. We're getting results that are particular. We're in a particular state. Whereas before, we weren't. The Schrödinger dynamics describes the evolution of the wave over time. So this is an interesting thing, because one of the issues with quantum mechanics and with most physical theories is that it doesn't tell us, the theory says nothing about what it's supposed to be applied to, right? It doesn't say, well, it's only supposed to be applied to particles. So technically there's no boundary on what we can apply it to. So this bothered some people, including Erwin Schrödinger himself, who proposed an unusual thought experiment in 1935 involving a cat in a box. And there was a cat in a box along with a container of cyanide and a hammer that was hooked up to a radioactive particle, and the radioactive particle will decay, but it's one particle and we don't know when it will decay. We cannot say for certain when it will decay. So at some point, it will decay, and it will release a hammer which will break the cyanide and kill the cat. And so Schrödinger said that, well, he thought, well, this seems kind of silly. If we take quantum mechanics as being literal and the wave function as being describing anything of any size, then before I open the box to see what's happening with the cat is both alive and dead at the same time, which seems kind of absurd. And this was sort of the crux of this idea of what we now call the measurement problem. I mean, it's a much deeper thing, and having 15 minutes, it's very hard to sort of squeeze this into 15 minutes. I'm going to add one extra little piece here that I didn't get a chance to add a slide for this, but then Geshe Topka told me he was going to mention Wigner's friend because I introduced him to the idea. So there's another experiment, a very curious one, whereas you could put Schrodinger and his cat together inside another box. And then you could be this guy named Eugene Wigner, who was another physicist, and you could ask, well, when has the measurement taken place? I don't know if the cat is alive or dead until I open the box and ask Schrodinger. And then Schrodinger can tell me, oh yeah, I opened the box, the cat's dead. Or Schrodinger could say, well, I haven't opened the box yet, so go back outside. And so there's this question, and this was related to whether Wigner was trying to sort of get at whether consciousness collapses the wave function, but there are some deeper issues here that Geshe Topka had talked about. In any case, this measurement problem goes back to it raises some interesting issue, and there's a very, very famous physicist named John Bell, who he made two comments which I thought were interesting. The first is that this concept of measurement becomes so fuzzy when we think about it, that it's really surprising that it even bothers to, like the fact that it appears in a physical theory at the fundamental level seems odd. Like, why would it be there? It doesn't make any sense that it would be there. And in another quote, he said, conventional formulations of quantum theory, and he also said quantum field theory, are unprofessionally vague and ambiguous, which is a curious thing to say. And I dare say that I agree with him on this point to a certain extent. One of the things that quantum physics is very good at is making mathematical predictions about what will happen in a laboratory. It is one of the most accurate theories to be developed. We can predict to several decimal places how certain things will behave. On the other hand, we have very concrete things that we see in laboratories, and the math connects to the experiments very well. What we can't seem to agree on is how to interpret that and how to talk about that. And a lot of this comes down to the measurement problem. And so what we're doing is trying to explain this idea. So to put it another way, the Schrodinger equation describes quantum processes, right? So this is the one way you can describe how a system evolves. Again, I said there is another way, but this is the one way we can talk about it. Measurement itself is a process, but it's not described by the Schrodinger equation. It's not in the Schrodinger equation. There is nothing in there that says anything about measurement. So, as John Bell said, why would any good physical theory have two different descriptions of processes? We have the Schrodinger dynamics, which explains how things evolve and the dynamics, we call them dynamics, how things change over time. But then we have this description of measurement, and this is a process, but it's a completely different thing. And why do we have it? And that is sort of the crux of the measurement problem. So most interpretations of quantum theory are sort of attempting to explain the measurement problem. They're attempting to work out why are measurements not described, say, like we have the Schrodinger dynamics, but they don't describe measurements. They describe processes, but they don't describe the measurement process, which is a process. And this measurement process seems to, we have this problem of it doesn't tell us what size it applies to. Where does quantum theory, what size does quantum theory apply to? Does it apply only to the small things? And these are all sort of issues that we're trying to work out with our development of interpretations of quantum mechanics. So we're way past tea time. I'm gonna close with one other thing that I really wanted to get at, and this is going back to what was talked about yesterday. Why do we care? Why do we care about this? Who cares? Is it going to help ease human suffering? Well, here's my answer to that. One of the things that makes us human is that we wonder, we question. When I was a child, I couldn't stop asking why. Why? And I still can't stop asking why. It's fundamental to who we are as human beings to try to understand the world around us. So, yes, there are plenty of practical things that come out of quantum mechanics. Quantum mechanics ultimately, not that you would ever do this, but it ultimately explains most of chemistry. It's fundamental to it explains transistors and semiconductors and things, but putting all of that aside, why do I care about this? Because I want to know how the world works. I'm a human being, and it's what makes me what I am. And I think it's what makes us what we are. So why should we care about this? We should care about this because we're human beings. It makes us human. It distinguishes us from other beings. We want to understand why the world works. And I think that's really important, and it gets lost sometimes. And I don't want it to get lost. So, Duc de Chez.
So you managed to finish in 14 minutes. So you gave 1 minute to Tapke, so that's good. Laso ane gela number lenji zu changma ane tuji che shue da damshi chinga changma tuji che shue in dine ngan zu da soje parsing di ane chu kamani shu sapshi chai do ni sum chu songa shipshenga la kamu chu chi nyur daung kesar ya jela ngan zu tuzu mangbu stanjin go zu ma to nen laso ane tea break until 10:45. So we are reducing or stealing 10 minutes from tea break also, not only from the
Don't look at me.
presenters' time.
Wasn't me.
Okay, yeah. Thank you, Tujina.
Thank you. Yeah, that was
and its explanatory power, and what science actually aspires to do, explains the world which we live in. The other connection determinism has it's with human free action. Even though I'm a philosopher, I will not talk about it, but it is connected also with the Buddhist concept of karma. The problem of free will and determinism is the problem you deal with when you think about the concept of karma. We will leave that aside. We can talk about that during the discussion if you're interested and so on. Let's just focus how determinism was fundamental or central in shaping our understanding of natural phenomena. In order to describe the world in deterministic terms, we first have to be able to actually completely well define the state of the universe at some time, the description of everything what exists, and also that we have the kind of physical laws that are exceptionless. That means they are always universally valid and determine exactly true at all time in all places, and they fixed exactly what's going to happen in the future. Well, all the time I am talking about the future, but it's not just the predicting the future. It's also, if we have deterministic laws, we can predict both future and retrodict to the past. So any fundamental theory which we are familiar with, which we know as a deterministic theory, it's time symmetrical. That means can explain, can predict what's going to happen in the future, but can retroactively also figure out what happened in the past. So, for example, we can predict when the Halley's Comet is going to come next time, but we can also retroactively figure out when was last time in our sky. This is what we call determinism. Theories that can do that, they have that kind of laws, we call deterministic theory. The good description or insight what determinism is, the first time was offered in the 18th centuries by Rudyard Bošković. 50 years later was repeated by Laplace with so-called Laplacian demon. But it exactly says it's called Laplacian demon because it talks about the creature that has enough cognitive power and enough knowledge about the state of universe at some point and all the laws. That kind of creature could predict that we're going to sit today or at this point, right now, who's going to be here, what's going to happen. That creature also could figure out what happened 50 years ago. Also knows who was how this program came about, everything. That's the reason it was called the Laplacian demon. But it's here in this description, that determinism, which comes from Rudyard Bošković, you exactly see that. Give me the laws of nature, give me the position, velocity, and directions of all particles, and I'm going to predict, if I have enough cognitive power, I'm going to predict everything what's going to happen. This is what determinism really is. So now our main question is: do we live in the deterministic world? To answer that question, we have to look what laws our best contemporary theories postulate. Are those laws such that they can do what I described? That they can fix exactly what is going to happen in the future and the past together with distribution of matter. You're all familiar, you probably heard about Newtonian classical physics, Newtonian mechanics. In Newtonian mechanics, it's taken completely to be deterministic theory, because according to Newton's laws of motion, together with the velocities and positions of all particles in the universe, I'm gonna calculate future and past states with absolute precision. Theory of relativity, the next well-formulated theory. Of course, there is a special theory of relativity and general theory of relativity. Special theory of relativity is more easier taken to be deterministic, but theory, even general theory of relativity, if you take it that is models the physical universe using different spacetimes that satisfy Einstein's gravitational field equations, could be considered deterministic theory. And then something weird happened in science. At the beginning of the 20th century, quantum mechanics. Quantum mechanics is a very different theory than any theory which we had up to this point. Why? Because it's for the first time we thought that we have a non-deterministic theory of the world. Theory does not predict what occurs in specific case. Rather, theory tells us just what are the probabilities for different outcomes. So these are very different laws that we were talking up to now. When we think about decay of radium atom, we actually cannot predict with absolute certainty when the decay is going to happen. If you have a chunk of radon, you don't know when particular atom of radon is going to decay. We can just have probabilities when this is going to happen. That's the reason when Ian was talking about the measurement problem and Schrodinger's cat, you saw this example that the vial of poison, when it's going to be broken, depends on that decay, depends on this random process, when it's going to occur. So in quantum mechanics, even if we have a complete knowledge of systems wave function, now you know what the wave function is because you heard from Ian. Wave function really is a mathematical object, but wave function describes a quantum state, complete quantum state of the universe at some point. Even if I have complete knowledge of systems wave function, I can only predict with certain likelihood what is going to be outcome of some experiments. I could never know anything with absolute certainty. Randomness, for the first time, challenged our traditional classical picture of the universe that is entirely deterministic. That wave function, evolution of that wave function is described by so-called Schrodinger's equation. Of course, it's called Schrodinger's equation because the father of the equation is Schrodinger. That equation is completely deterministic. But even though the equation is deterministic, it actually describes evolution of the system just in a linear superposition of different states, of different states. So when the cat is in the box, before anyone looked, observed, measured, before anyone opened the box, if we have only wave function, that cat is in the superposition between being alive and dead. We know we never observe the world in superposition. Our world, which we observe, is always in a definite state. Thus, something is wrong here. Einstein noticed that immediately, and so on. So the problem, this is what we call the measurement problem. Philosophers, at least, always used to call this measurement problem. And that measurement problem is how to get from this wave functions, physical theory. We have a superposition of different sides of this problem in front of me. So one possible solution, which sort of was provided at the beginning, mentioned several times here, that during the measurement and observation, what is the indeterministic. and know in which of these possible outcomes, these probabilities are determined by Born's rule already, which Ian mentioned, and also based the system's wave function. So now when you know what is on the fundamental level in quantum mechanics, you have to ask yourself, is that the world we live in? Is it really now? We got the answer. Our world is not deterministic, our world is indeterministic. Well, that would be too fast of a conclusion. It's gonna depend on how you interpret quantum formalism. As is mentioned, we don't know still what that theory tells us, what is on the fundamental level, how these things all work together. So that's the reason we got in the quantum theory these different interpretations, which are really different quantum theories. And depending on these interpretations, we're gonna say, well, anyone who thinks about fundamental problems would not take it any seriously, despite what Tapke said, namely that what causes collapse of the wave function is somehow my observation, conscious mind, which immediately you think it raises a problem. What happened with the world before there were any conscious minds? Or what Einstein would say, who's going to collapse wave function? Do you have to have a consciousness of PhD students in physics, or mouse can equally collapse wave function? So this Copenhagen interpretation is indeterministic interpretation of quantum mechanics. It's not really good physical description. There is another theory which is equally has non-determinism, out with a much more acceptable physical description of collapses of wave function. When do collapses occur? Randomly. For no reason whatsoever. They just happen. Because of that, it's a much better description of what is going on. But in its core is a complete indeterminism. Then, apart from this, collapse theories, Everett's theories, that's the reason there's a picture of Everett. In Everett's theory, wave function doesn't collapse, right? We said we need a wave function collapse in order to get the definite outcome. Well, world splits. There is one world in which there is me and life. So this is a many worlds in this, doesn't have any randomness. So we can say that then we have something which should be familiar, but he says he was his first science teacher. Dilemmas, do we deal with the waves or do we deal with particles? Bohm says we always have definite positions, and mental theory, the future positions of particles and velocities will be based on wave function of the system, and particles, this initial position and velocities, which particles really have. So that theory is fully deterministic theory of quantum mechanics. So what we saw right to this point, that quantum mechanics is open to both, the quantum formalism is compatible with both explanations at this point, because we have theory of the world we live in. Good. So now, just at the end, we already talked of the most important experiment in quantum mechanics, at least Feynman said that, is the double slit experiment. In double slit experiment, which was already mentioned here a few times, you had a beam of particles. It could be photons, but it could be electrons, it could be larger particles, is sent through two slits, through openings, and there is should pattern in life. What George was talking about today. So Beyond barriers that they already described, that is the textual screen that records where the particles arrive. So now we can have what happens in classical case? What happens in classical case, if I fire tiny particles to some slits, what's gonna have like a paintballs? Each is gonna go through each slit, and we're just gonna get ends on the screen behind each through the door. If I open one door, right, I'm gonna get a band of where these paintballs landed on the detector screen. If I open another door, I'm going to get another band where these particles end on the screen. The question is, what happens when I open both doors? Well, you would think you're going to just get those two bands where particles went through the door, or paintballs went through the door. To describe that, when this spreading causes their interference. That interference, what that means, if crest of the waves meets the crest, they're going to be amplified. So this is constructive interference. Where crest meets a trough, they're going to cancel each other. So now this is going to call the destructive interference. This is where you get this dark thing on the screen. I already showed you. Quantum case. I shoot particles through the two slits, and what happens? Each particle, in some sense, right, you would expect if it's just particle, it's going to go through the slit, and that's the end of the story. We're going to detect it just as in the case of paintballs. But what happens is we end up again with the interference pattern. It seems like each particle going once when you fire lots of particles like that, you're going to get your standard interference pattern, right? First from individual spots on the screen, but more particles you shoot through the screens, you get this interference pattern. This very important experiment could be described deterministically. What pattern you're going to get depends on the description, very precise initial description of the system. But it can also be described indeterministically, that spot can form in different places despite you having the initial condition described. The same initial condition could end up result in the particle being in different places. So, before I say thank you, the conclusion is, at this point, we do not know whether we'll live in deterministic or indeterministic world because we don't have a finite theory of the world we live in. And just a comment, like everybody else, why do you guys, in your Buddhist studies, now on top of Buddhist studies, you should study science? First of all, science, but of
gen Vishna la pujiche shueda ta dijela ngazo nyamshu thumeki ane khokapdi duschiche ane gozugi chedan trinki jushi di ko chedung gamrik basya da tindiki jushi dis khothakbo yowada tadub da dewa yobeki nesu mangbuchi legi yobeki kyumzen tene ane ngazo gyuriya di nema ngazo namgu alternative chigjil chig gyuriya mato ane tanda radio gi june da thakar gyuriya di ane duschiche chime dimba sonza ane gela number lenje so ane thiwa kuye khokap nyungwa rairwa cheza dila jo sambal thiwa yakbo dinde guro chima to choshida mi ge dinde maguro ches.
Thank you.
Lano
te tante dug chana du la lab la chi sona gdo te du thanche la lo mar sang gdo du la de lo yoba de du ti churn ro du ko yam cha du la ba long du te ko lab te ni de ne tante te jora ngar cho chi gi chan yin chi gwe chi 다르라는 가서 남아선 제바 되배 망가와 시당라 소바때서 죄배 망가와 제바이나 야 두샤기 또는 자만저 자마시어 몸을 내기래 든디기 또는 거기 너가 제사지도와 계시 너가 매바이나 제거 야전 로야 요말 마차 야전 로야 머 소소기 시제 야전 로야 요말 너가 배셔 땅에 줘라 유들 천재지 고르서 그도 대제도 말에 어떻게 또는 깔린지소로 나셔
Yes, then it is more lighter kind of elements or
nature to it. I would actually phrase it as there's nature to it. I would actually phrase it as there's a system, there's a physical thing. It's true experiments we have found no limit. Scientists, even beyond atoms, molecules, even maybe beyond molecules into larger.
suging ngopo chika jigo chungwa yamana cha den zo ting la yue ding ke ane rakba jigo che den zo ting la me ding ke den ke je mares tende ke je jing ngopo tamche la yue yamana dun jing ke du yo wa den ane ke le la ru du yo res che ta thanda yim be na nga zo dun jing ke je da yo ane nga zo ke shai mares.
It's while so George is right. We have not. We applies to. It's just it's a theory, and we don't know where it stops. There are scientists, good scientists, who believe that you can't describe the universe with a wave function. They think it's an absurd concept. They think it's absurd to be able to describe cats with a wave function. I think, and so. The reason I wanted to point this out is because there's this I think people think sometimes that it is up to a point. One of the things that keeps me employed is the fact that we don't know everything, right? And one of the unanswered questions is this, and there are some scientists who have one opinion, and there are some scientists who have another opinion, and hopefully sometime down the line, we won't be able to settle. But I just want to make sure that
chata dela chik nembe jaw samsung sedung ngam rikbe ke nanglo la ane neju mangbo shi do as ngobe ke nelu dan tewa yobe nelu dan tewa yobe ke neju mangbo shi de deni bena nelu di dereda se che tha cho ki sansam le da wa chi ke che shi mares singen de yores chata da dela du sambala sedung ngam rik ko dreshe gyak tang che do la so sha wa jere ma ruas che su ke thimu mai be ke ane dreshe gyak
so ta gegen da getu ti nge chwa de ta danda che dung khon ri bare ti indu ti nang lo le ya ta nga chue ge ha le ya ta nga chue ge ha jang ge ke chen bo shu bu chi chwa ni ji do ro la de ha ko jang ge ke chen bo shu bu chi chwa ni ji do ro la de ha ko be the fundamental particle de she go ba light che za nga chu mi ge lung thong thong yo ma ba che za ti indu lung de dang danda we du ni le ya pe na nga chu lung de shu bu chi dang ga chen bo labar de nga chu nang chu go nang lo le ya hardware the software ko she chen hardware the software ko she chen ani nga chu dam da thong de go ba che za di ko ten de ani nga chu dam da thong de go ba che za di ko ten de de interdependent cha de go ba de de yin de danda long me bi na single ga chi ma ba nga chu nong chu go nang lo ani mil pe sha go ba kam ba me bi mi de ge
tewa sun de la
ti nge danda chwa de ro ta de nenga chen bor da ti chwa de tang bol nge ti ge karsa sewu shivuji meba ina lente to marwa cheza ti inde ta tanda nge ki karsho war se dola rowa da longi lundal dang gwe dul ge longi gwe do karchin ka to yo mares rowa lundu ge gwe do karchin ka to yo mares ti inde gwe do song so wala tanda o ma de ti ani joba yo mares ya ta ge ngachu ten dur ta pa sha go rowa cheza te da ani yes plus 2
Okay, so two questions, okay? Slit. For the question, first question is, so when we talk about the particle physics, so I think that there are two most important particles. One is the photon and one is the air molecule. So if we understand air molecule, that's what I'm saying. When I say I'm in his place of mind and without or interfere the travel open to everybody, and the size to be there since the beginning of the universe, at least. So even though we cannot say that protons are permanent, non-changing ever, but for a very long period of time, it can almost stay like
check.
Yep.
Last night, I went up to the roof of my hotel, and I met actually Professor Chris Impey there. It was about 6:30, and we looked to the west, and it was a clear night, and what did we see? We saw a spectacular sunset. And we marveled at the sunset. And I invited you to dinner, but you were busy, so I went off to have dinner afterwards. And what does the sunset look like? It's quite red. And then another part of the sky is blue. That is exactly what you're saying. It's air changing the path of light. Depending on the color of the light, it's affected by the air. The magazines that go to the moon. He was to Mars. And he said, well, George, the strangest close. And sometimes we don't know it. But in situations such as the moon, where there's no air, they find it.
다 gelagi tiwa thangbo jorwa di nobkucho ke namka di khado maure de shas di khachini cheware sedu zambala ane wedul sigune re we joya dila lungki duki shubjen chewa am timit the one who went Harrison said yours just kora ane dawe giteng lan tongking ki mi ki nanglo nyam to kama sa mingmar da chik dinde galan joya yimbena ane di kapsule ende ji surgi re samya ki ta ko samlo khorya ki chetula kerang ki keje kharshya yule sambala korang ki khallas la yimbena ken sashu di ane ngaro nyering kin dushi lol shartan jorwa dipe de manda ware shas dawe giteng la dos te du sambala damla yowa do chi yimbena ko pet tharang bu shiu yimba thongu dos la sons ta di khachin chigi ore sedu sambala ane dawe kiting ki ane lungkham kin rotang deda ngazu zambuling kiting lungkham kin rotang di loga yimbe kyomsen tene ane we la khacho gyurtan da we la tangzin chetang da mandaw indu ane loga chawan thong yores ngazu zambuling ki nanglo la ane lung ki ke we la ke chigi mesar sam goya di chitang lungkham kin rotang rawo yewe kyomsen tene chebar den thong yo shirang thong me wores cheta da dawa da dene ting yimena ane se thong yores kirangidi
지당 견라 콘서트나 야에 네 당기 지당 등 안주 답변나 뒤참모데도 갑갑을 안주 미다고 되셔야라 펜도 요레스 뭐 대도 나란주 대동에 갱코랑라 계자 양자시 찍고 있나 it's like without interaction seems to be no decay even decay is very very long so argument is here is that in Buddhist permanence everything is impermanent at the momentarily change and then
There is a free proton which has theoretically the half-life that's longer than the age of the universe. Now, if I had a room full of protons, so how have trillions of protons, just enough. The statistics allow us to predict the half-life. And the half-life might be the age of the universe. Now, we don't actually need to see many things decay in a short time. It just means that if I have a kilogram of it, then after a million years, I'll have inside a nucleus. They actually decay all the weak and strong nuclear interaction.
The gelangi tanda podudi bembena ya weak nanglola ane decay se da se romando se sengur se ke tanyeng mang zo pejur chigiwa chaza da se mase ki keje shedu sambala zo selu se tani keje shegu yores selu se tan chik tanda ngu girik den zu keje se ka she tang zo jigden kham ki ane tandeng ngan zo jigden kham disi yordan jigden kham di ge ane ta chesel ringwa den ki keje shigi yodu sambala ane di ko che ki thuyule den ane rawang chen ki ane product thangka di ane pad ya mangbo shiuji हाँ साया के चले के मंगबो शिवबे बना अने दीग नंगलो ने अने खंगरुंग ची की अने ठंगा मंगबो के वसना मारे सिगियोर त दुनथें के नंगलो येबे के तंदा तेदु के नंगलो येबे पोदु दी ना अने नामशा युंड ने को सेंगुर डोंडो बरेस कोन सेंगुर दुगी अने पोदु दंजो अने मनिंग के दुग ngो सिगियो ngो न्यूटन से दीग दुग ngो ला अने पान जुर के छेदु योरे से वर्ता okay Chris and then Wanda Chris and then yeah Okay, dijela chola soinda kasani tangmungene gyabla yoache nine ene lawa chanya nyu yimba sonza khuzul ko kapuinda.
So I have a short question for Vishnu. So it seems like to go beyond Copenhagen and wrestle determinacy from quantum mechanics, you pay a heavy conceptual price. You either proliferate parallel universes with many worlds, choices in those scenarios,
I think at this point, quantum. Copenhagen interpretations is not a description of when collapses. And on the other hand, you don't know what probabilities mean in that, because how can you have probabilities in the world where everything is realized, right? What does it mean? Cat is 50% dead or alive. They're alive. There is a world it's alive. Everything is realized, right? So there is a world it's alive. Everything is realized, right? So Copenhagen is out anyway. We are trying very hard. And there are waves. Not wedded to any particular theory. We are trying just to figure out which of these different theories that are offered to us really give a close to physical, but I think Copenhagen is just.
Any ngol yores ya ta di jesh so do da diga na shi ane lab ge chele shik ba se ki ane nezu sawa de ane lab ge chele shik ba se ki ane nezu sawa de mangbo chi gya gu yo sonza mangbo chi gya gu yo sonza di ane ko tunda mesala so kangete de di ane ko tunda mesala so kangete de wa do chi mende wes 아니 모랑게 칼라기 요르세도 삼발라 대가랑 레스 제가 아니 다 대금스틱 아니 다 대금스틱 아니 다 태본 동금에스 제가 아니 우연히 수치 태본 동금에스 제가 아니 우연히 수치 비임베나 아니 직답 비임베나 아니 직답 대외고 토네 아니 랍가 장신 데 여데 남 대외고 토네 아니 랍가 장신 데 여데 남샤 레라우딘데 요레스페 와 남샤 레라우딘데 요레스페 와 남샤 시기요와 줄링게 마레스 남샤 망부 여웨 남샤 시기요와 줄링게 마레스 남샤 망부 여웨 낭로니 따드르그 삼루 땅땅 그 토낭로니 따드르그 삼루 땅땅 그 토네 가레 테사레다 마 테사 마레스야 디게제 신인도 삼발라 보문기 데시 약단도 빼탑데오 아니 레라오 약보든데 아니 통구도 산단도 빼탑데오 아니 레라오 약보든데 아니 통구도사 okay then wandala and then I will go to the
망게서래 다나 조자바 참만은 소리도 제네 내가 다나 대가를 체등이 공 경우sol다 미세 저 미세 탄데 샤메로와 아이나다 실지도 그저 과거에 니도 급하다 세리사주 참만을 짜이 디디 체등이 공 개개 몸벌 가서 저바를 용대 그러와 디지다 콘솔 내가 간디지 자기 메다 갈아가서 쳐보태거든 디지 링게 단다 게지 탄게 라스라 게지 탄게라라 저바이로와 진세 가르르잖아 다다나데 가서 캐모캐서 몸 패대리 봐 삼매가 동시비시 난게 요래 세등인 코데 가서 나지 오세도 쉬고 다 탄로야 바다 순대 걸어 다 다리네 게지 탄게 오늘 지가 쳔보래 비무세 야보 요러 봐 디지등에 게실라 태가를 줘 봐시 다다나 가서 소징인 코데 니보마베 따도 tum도 와데 나봐서 챈데 걸어 봐 그때에 다다나 가서 세등인 코데 아니 보세 그 배는 제글로 니수제데 들라메스 봐 참매가 대체 참모 시시가 요래데 찬매가 대체 참모디가 라시데 이 자반이네 매된게 그러와 이 자반이네 매된게 덤보 마이게 덤비랑술은 대된게 도시행도 잠발 아니 저러면 코로고 있다 디나로를 돈이 요러와 근데 이나를 수치는 대한으로 도스 돈이 제대로 될 거로 내자 요러와 다 저러면 니보마베 그 전타데 다 세딩이 거도 많다 봐지 고 맞아마 예와 제저러 오세 다트 던게 예나 오세 그 유용가 나로라 더참에 라시데 템베 제요디 체드니네 저러면 가르 저두세나 더 참모디 인지미지 덤비랑수도 내가 그랬어 다디 로스 센스 비주도 수치 몰래기도 와 다 대체디 아니 더 참모그 랑시데 덤비랑수 고 던체그 랑시 녀바도 그리스 드얀데 소징이 거 다더래도 와 세등이 거 놀다 녀메 랑시디 시인도 라지 랑시 시인도 좀 더지 랑시디 시고요 말아 대체디 땅에 저박하도 되다 세등이 거데 우세도 터세게 야나 우세그 용그 나로라 더 참에 랑시 템베 제요디 녀바도 더 랑시 고 덤비 랑수데 녀바도 그르스 슈치모 드데 치다 아니 제도 되게 녀메 용그 놀라 때 금마레스 봐 던체그 랑시는 대대와 수지 랑시는 대바르스 저기도 대지데 다 기실라로 디투라 공스 칸데 얘네데 세워주스로 치스 와도시
저 지난 어제 세워다고 쳤으네.
저와도 도지다. 세등이 거데 나지치는 간수 아니 현도 더 참이가 참여가 더 라시 템베 제요디 니준제데 더라메에서 더 참이가 라시데 그게 덤비랑수는 세고 용가 나로라 동배랑수는 지금 말했어. 저도 동반이도 들어봤다. 동반이 끼지 들어가러 봐. 대체도 코니 단다 뒤에 쳐서 셰데 동반이 말했어. 그 이지메지 덤비랑수를 그걸 해서 휴지 뭐 들어도 와. 원다데 드얀데 아니 세등인 거도 딱 간지지는 통보차기요. 뭔가 됐어요. 좋아요.
뒤처럼라 입유메 될라고.
다 쪼고대요.
직당게 딱nga 단다 서버랑 정마서. 니송주도 둘라메세야데 너데베기 페지 단다디 되바 인삼데요. 가인스나 너데베 입디 딱베 소리지 간제 데멘두제 소리지 숙제 멤베 소리지 저랑데 도단 제비나 입디 똑다 진짜 페지 직 입샤 미투베 소리지 양나 샤비나 똑다 샤고베 소리 직체 다디 찌기 용사딘다 니송주도 둘라데종 안주 둘라 입요레 요마레세야데 뒤차랍라야 듬베 입요바 송바데 심자메 숑카직라 요바체 뒤타란 듬보 인고 바티체 첼라 이메 디기 차네 고 페나 마리다 도티베 따용도 입데 레레 야야야 어디도 다 제바면도 다 간데 딩가조 베데 다 가서래 철어난 게 저바베 십자고 된데 지 차드샤 데 내가면도 당에 계제데 베지 반부체네마 슈긴이 딩가조 지당가조 단다 제등원감데 당보 미팅 바베지 슈바이나 니마가 게레도 tumbu konzo kapchig la ngal dinde sigdo tumbu shedan di chanzu gite zo da dezo deshe ja du mu tu ni yongya dile tumbu ne ya ko ngem ta se jor wa sedu se dini tumba mendu es ane dinde se ne ya ko dojo ne zo ba jap chogdo 강다리야 딱 내기 돔딱 내 갱게 데래 저와데 베 칼소 빼제 띵나고 제는 갱 티장에 차상지 렌테마서 이나야 지용게 렌데 가르자고 해서는 넘버 탐제도 툼바데 자원에 말해스 제동원감 세력이 간족의 유전기 내 당기 수주 제샤 유전기 개발에 세야 되라야 건조 단다디 유전로 섭다티로 유백까지 되다 로이 딱당기 차네 제제지도 장래야 똑바에 따서야 되다 건조기 유전기 숙전 세야 되게 람산 직발레다 매와되다 세버레셔 저단다 돔데지 쉬와이나 단다 게랑게 되와되게 태게 랜딩에 슈트마서 지용게 랜직다 고 탐제 대대we 진짜 동매직 쉬와이
So just briefly to translate the discussion, the questions was when we talk about these fundamental particles or the partless particles in the Buddhist traditions, the Vibhashika and lower schools they talk about the formless nature of these fundamental particles. They don't have a particular shape or form. And then the higher schools like Madhyamika, that is associated with fundamental particles. So if that is the case, then normally when we talk about the quantum mechanics or the quantum physics, people say that quantum physics is more kind of in tune with higher schools like the Madhyamika and mind-only school. So what is happening here? So Geshe-la is like overlap quantum physics with Madhyamika or the mind-only school. There are some angle in tune with Vibhashika or the lower Buddhist schools. Even in our concepts like this measurement problem, where the measurement or the observer is doing something onto the objective particles. We are actually in quantum mechanics or quantum physics, we are talking about changing the nature or the results of that objective reality. But in Buddhist schools, in like Madhyamika, we're talking about our perception level, how we perceive them, and not much about what our mental projection is doing onto the objective reality. So that's what was the discussion. Yeah, Tsumatsu, the Gabla.
So thank you very much for your presentations today. I personally am very interested in quantum mechanics, so it was really a pleasure to be able to hear different perspectives from science and Buddhism as well as philosophy as well. So my question was about quantum entanglement. So I'm quite interested to hear about your perspective on how quantum entanglement works. And from your perspective, why do you think it works in that way? How can one particle in one place explain quantum entanglement at this stage?
Chola ki tiwa di ane tsedur zingtil lai jo yore ngansu entanglement se di ko le re de do cha di ki tiwa di ki che du la ningung gyab ke soden gen team ki ane tak kama chonge ringa la chola ki thiwa de la lengeng res tim basonza ane konsu ki lengya mo wa chesa. Next question please. Answer to the nuns
space like do tongcha ruchi di chi di gala namka di ke the space land do tongcha di meba chae di meba gor cha da namka meba cha la di yor yo mares ro kisi namka di meba chae yo ba ina namka di meba ne kapla ni dugi ne pop di kanjes ani du da namka tongcha diang ani koran du la tene shage yore du mena yang tongcha di sha tu yor yo mares 디 저쪽이 아니 이것도 다 비지지기 심이기 딱지 치지 심이디 시어를 요 말세줘라 디 딱지 칭이디 딱지 칭을 알리레스 와 딱지 칭이기 딱지 마치 봐도 심이디 시요 줍다 뭐 줍세디 아니 가정갑 중갑주로다 찬염레스 와 시여스기를 메시기레스 대나 딱지 지두갈 그 시샤스라 그러 제가라다 그 딱지 칭에디 율레 라테네 샤베 소르지 근데 아니 다 그 딱지 집에 잡아요 여러분 잡아대 다 상마 수 dom제 심이디 시샤스는 다 쳐봐 디바도 심이시와 랍도고 말어 메디고라
Okay, so first question. Okay, so first question is for Geshe Tapke. In science, when we talk about particle and space, we need space for the particles to abide. Space is permanent or not. Whether there is a time when there's no space and there's particle. Is it possible to have a time when there's no space and there's particle? And if yes, then how? So if before you look at the cat and the probability and the cat happens to be dead at the moment time at that time, can we say that that observer killed the cat?
저पे 야고도 다 남가다 와레고 동사 매베 뒤자요 말에서야 소리지 차기요라 나이나 갱 뒤와 댕안조 단다 당기 인간조 남게 뒤세야 될 디 남게 뒤세야 될 군두능이만에 배추 통나난디 망보 체력 발라 송낭기도 자자 디 인간조 더나 최고야 제 인사를 삼고도 또 중국이 중나라 단다베나 남게 뒤세야 될라야 드셰 자당라 베나 다장로 저에 두고 대와 요래 개두제기 중국 직전 요래 안에 군제 따라 나다기 뜻 나로라 따위나 네마 동연도 뒤차장 사추 멜롱 디네 팀제 딜레 타웬 중앙직라 마 팀제 마음바나 직된 사바 차연도 양고 뒤진이 누바소리 제대 딩랍기 생리게 자다디 더나 제고야지 두 인지 뒤뒤데 자단다 디 남가디 셰비나 간조 공바저 나라 부가 남가 세야데 ngobonaala tsegirewa nganzo khamge nalo la ya phuga namga seya de nanda mumba tha yin lo seya ge tanda lo le ya ane mumbe du seya shedwa ta tserik nalo la tangi nge das dewa ta bre dark matter the dark energy seya de labge yore yena khonzo dark seya de nakbo re seya thanda da mare khonzo garchon mishibe 직 캔사지 여바데 미시바 인자 내가 명다네 안에 나고세야 된데 다녀다제 뒤 나고세야 된데 다 하먹어야 뒤 텐데 여바 저장 디지털라당 먼저 텐데 심죽 제고야지 망고도 삼당에 책령 붙여도 단다 딩에 심미디강 책지需求지 심미디가 나에 다다 자자자 고쳐마다 이내 나랑 삼적 전에 슈랭가기 콘솔라야 개디 대따르나 콘솔 가르쳐 거래서는 뒤직디 딱제 심주칸나라 천제 마체 콘라 랍다 뒤니게 랑신라 내요레 세겨와 아니 슈랭가게 됐다나 딘데기 다 내가 녜메지 요나 딘데 심미지 요이나 지시와다 선바니가 레베스 다 디치고레마도 딱제 젠이 비게 딱제 간나라 단다 경원 체리나 시제 심미지로 데 가상직 시와다 딘데 게자다 잔이 세게 요사 말에 당한조 인지게라이나 hypothetical situations들이 개디 됐다나 안에 텐데 인고도 시미디 시와다 선바니가 뒤타무직 랍다 뒤니가게 란신 녜메 단다디 슈퍼포지션스 해야 돼 네디요나 디 시미지게 텐데 인고 마시다 겐콘즈 다디 응에디 가르사 저고 제베서리 쳐서 공개해
Okay. So, yeah, you want to translate.
Space particle. So this is according to the Kala Chakra tradition in Buddhist Tantrayana. Space particle is a concept that is associated with Kala Chakra. And then when doing my presentation, I talk about this space particle. So this is also something that we need to think about, because when in Buddhist tradition, and there are, even in Kala Chakra, there are some different versions of it, or the different commentaries of it. And also His Holiness a very subtle kind of like an element in which the four elements, the elements of the universe, the physical universe, can dissolve into when the universe ends. And also, when the next universe happens, it is also the element from which the four grosso elements like fire, earth, and these things can emerge out of. So these things I'm not making. So in my presentation, I talk about in Buddhist tradition what we call the dark science. When we talk about dark matter, it's not talking about phenomena is not observable to us. And so because of that, we call it drug, and we don't know what dark matter is. So basically what I'm saying is that there are many things that we can speculate and think about.
Can I say something about Schrodinger's cat really quickly?
Yeah. Schrödinger cat. He also said few things. I will combine both of them and then
Okay.
translate.
So regarding Schrodinger's cat, I think that's a great question. Did Schrödinger actually kill the cat? And this is something that actually puzzled as collapsing the wave function. That's one way you can think about it, as collapsing the wave function. The question, of course, is when does the wave function collapse? Does it collapse as soon as Schrödinger opens the box? Does it collapse when Schrödinger's eyes see the cat as alive or dead? Meaning when the photons that are bouncing off the cat reach his retina? And this was kind of why Wigner came up with his idea of Wigner's friend, which is he said, if you imagine Schrödinger and his cat side, and then he opens in Vishnu's, and Wigner comes in, and Schrödinger tells Wigner then when.
Again, Ian Koraningaki any Shimidan Jeviki land so domche any Jurgindarwa. Chazada Dindiki Tiwadi that Tamugan Tabila Karsung Reslavimena. Ane Shimidi Ngusunganzu Tanda King Taje Khan Lola Tsu Kiche, Aneko Shiva Reda Mashire, Sia Di Lagio Mares. The Kajin Lagio Sedu Sambala, ko Samlu Tache Tony, Tanda Lab the Duke, Nedan Ding to Temate Capsula, Ane Lab Chile Shing Mashisia, Di Kadu Hakumewa Di, Ane ko Koransu Namgur Tanta, Chawachitan, Denzola Teyun du Sambala, Ane ko Koransu Namgur Tanta, Chawachitan, Denzola Teyun du Sambala, Ane ko Lab Ganzuki Tache Nanglola, Te Savik Jela, Yamena Obu Rugby Namgur Twen Savik Jela, Ane Ninga Yinding Kinchi, Medu Sambala, Ninga Yinkene, Menkenchi Lama, Candes Chagiore, Kaduchare Maris, Kejashi, Nangshin Lama, Candes Chagiore, Kaduchare Maris, Kejashi, Nangshin, Teganangshi, and a Shix at the Schrödinger Tokpo, and a Shix at the Schrödinger Tokpo, and a Wigner Koran, the Wigner Junkin D, and a Schrödinger Hindu Zambala, the Kogun Tevi, Mana, Shimise Masikeja Shevimana, Senken D, and a young Susu Chadero, Wigner Koran Chadero. Wigner Koran Gesere, the Schrödinger Gesere. Yan Schrödinger let you Gesere. Yan Schrödinger let you Schrödinger Gesere, Koran Koran Shidi Yorsia, the Zuke Kandama, the Dikar Schrödinger Gesere, Koran Koran Shidi Yorsia, the Zuke Kandama, the Dikaris Lavimbena, love the Duce at the Chadu Yoris.
Yamanda the Consular and Anzo Tango Ludits and Didua. Konging Yema Samlota the Chrono Karech Tanya, Chronon Siduzanlea, that Namge Duda, the two. Tangazu Karisana do gola Sedu Mango Chera. 다 뒤에 페이지 tumbu 채널 tumjo리샤 직전에 남가에 tumbu 채널 tumjo리샤 섬 상로 망고단데 왜 가는 군두 제가 자도와 다 군두인게 디 거지 송두장 그 메시지도 군두인게한테 섬던데 꼭 주버지 가부총 dia namge du da de ko la de wa de yu sar shi.
So if you are interested to know about space particle, then there's a story about David Finkelstein, one of the teachers who used to come and teach us. He told us that he was like constantly thinking about the space. So he thought that if there is a fundamental unit of time and fundamental unit of particles, then there has to be a fundamental unit of like very happy, knowing that he was not the only person who was thinking about the existence or maybe the possible exist to refer to the fundamental units of the space or like that. Laso gela number lenje so tuzu zobe ki chen che ene nga zo ningung shela lunch break di shao keso ane ningung chusu ane niwala ya rangcha zumro chi sera ji shue du ane zidu ngam rikba de go nyok ba da ting sabo ta ru bu chane ane dewa shuk chen bu yun ki yin ba song za dewa mang bu ane kera kind of thing then